Reset. So I just want to celebrate various ways of doing functional programming in hardware and some of the people, and we'll have some kind of random digressions and perspectives too. Oh, there we go. So, machine learning chips, they're used to accelerate inference and training, and some of the hottest commodities on the planet, quite literally. And recently there was this deal between OpenAI and AMD about swapping equity for chips in some kind of complicated manner. These things are so valuable. The deals for them done at nation-state kind of nation-state levels. So the design of these chips is like a super important thing in the world, and I think we should care about them. I've worked on the design of 2 machine learning chips. These things are called like tensor processing units. This is an early one from Google, and I also worked on one at a company called Grok as well. And these chips help to especially make inference tasks go much, much faster than running on a processor. And the main competition are GPUs from NVIDIA. The one that you saw at Google, the one I worked on there with Lambert in the front row, was done entirely in a functional hardware description language. And the one that I did at Grok involved making a compiler that was significantly written in Haskell, and functional programming was used in its verification. I'll say a bit more about that later on. This slide shows you typically what a chip layer of a TPU looks like. This is the first Grok chip. And a key thing I want to point out, it's a kind of highly regular structure. You don't have like random gates strewn everywhere. You've got replicated blocks laid out in rows and columns. For example, on the left and right of the chip, you'll see these systolic array multipliers, each which multiply 320 by 320 elements. And I think the functional programming techniques are often very valuable for me to express these kind of replicated blocks, being able to reason about them. They have nice inductive structure. These chips are incredibly difficult to design. One of the most challenging aspects of the design of these chips is the design verification, DV as it's called in the industry. And most DV is done by testing, by simulation. So engineers write test cases and then they look at waveforms and try and work out what's going wrong. It's a very slow, difficult process. It's not quite unusual when you're designing a chip to have more people employed on the verification of the chip than any other part, including the design of the chip. And often, this design verification phase takes way longer than any other phase. So this really makes it hard to get chips produced in schedule, and it makes it hard to innovate new designs and try new things. Because every time you try and change something, you have a complicated verification hit. The industry is really hurting from this. It's one of the biggest things which stops us from making new and novel chips faster. And I think there's an opportunity here for us to devise a different way of designing these chips. And I hope to convince you that this different way should involve functional programming and formal methods. I'm going to show you some actual wee designs done in a functional language, and I've implemented and run them on this FPGA board that I keep at my desk. So normally, I used to come with the board and I would plug it in and I would like run a wee demo. But I just found it really hard to get these through airport security, because they asked me, what does this board do? And I'll proudly proclaim, it's an FPGA chip. It could do anything you like. Halfway through the flight, you can make a new circuit design and download it and run it. Isn't it fantastic? I feel so proud, but airport security were not impressed by that answer. And I was already on the US no-fly list for 10 years, so now I bring you this picture instead. So another thing I'd like to highlight is the enduring power of the digital abstraction. It's been hugely successful. Abstracting voltage levels on wires to zeros and ones and using Boolean logic to reason about sequential circuits has been immensely scalable. It lets the design chips of billions of transistors. So I think that's quite fantastic, and I don't think we often pause to think about how amazing this simple abstraction, how powerful it is, and how well it has scaled. But like all abstractions, they have their limit. The digital abstraction is an abstraction, an approximation. And digital circuits only live in our heads. The world only has analog circuits in it. And so when we think of ones and zeros, really under the scene, it takes time for a signal to rise from 0 to 1 and 1 to 0, and it isn't totally flat. It's all kinds of noise and so on. So when we stretch systems to a limit, let's say we try and toggle too many transistors at the same time, even though the circuit should work at the digital domain, it starts to fail at the electrical domain. Abstractions are wonderful, but we should always understand the limits of our abstractions. So, how is hardware designed in industry? What's the current, what do most real engineers do? Well, most hardware is designed in one of two hard description languages, System Verilog and VHDL. And here's an example. VHDL is the much superior language, a very, very good type system, lots of safety features in its types to prevent you from making mistakes. It's way more sophisticated than the other language, System Verilog, which has got many problems and issues, as you're going to see in the coming slides. So, of course, the industry has standardized around System Verilog. We're designing hardware, so I guess we're thinking in some kind of breadboard or Lego kind of manner. You've got one gate, you've got another gate, and you might like to compose them together. And this is straightforward to do in most hardware description languages. Here's like a NAND gate. It's written in VHDL, my preferred language of the two. And I just instantiate an AND gate, an inverter, and I wire them up. And I used the names of the wires to connect things together. So notice that the output of the AND gate, this wire E, is the input to the inverter. And that's what forms the composition. And all you're really doing here is drawing a circuit graph. That's all that's happening. This is the same description written in the System Verilog language. Again, you see the E wire going out of the AND gate and into the inverter. And you might have some intuitive feel what the semantics of these circuits should be like. So that's quite straightforward. We have a way of assembling bigger circuits out of smaller circuits by composing them together, just thinking in terms of graphs. So we can take that description, we can give it to some tools, some Xilinx tools, and they will place and route it, and you can see that tiny blue dot on the left, that's where it ends up. This is on a Xilinx FPGA, that's the FPGA that was on that wee board, that's on my desk. And if you zoom in, you can see the two gates, the AND gate and the inverter, you can see them wired to the pins of the chip. And when you zoom in, you see the gate, the AND2 instance and the instance connected together. So we have a path from going from circuit graph representations down to an actual chip. And then, but that's not actually how most hardware design is done. Yeah. The main way of specifying hardware is to specify a collection of concurrent processes, each of which contains sequential code, which is algorithmically executed in a C-like manner. These concurrent blocks listen to events on wires they care about, and then they fire, potentially updating other wires, triggering other concurrent events until a fixed point has been reached. System Verilog and VHDL, they're really input scripts to event-based simulators. And here's a simple example. It's an 8-bit counter with an asynchronous reset. Whenever a clock signal rises from 0 to 1, a clock edge, this code will run, or whenever the reset pin goes from 1 to 0, it runs. And what happens, if you set a reset, you reset the counter to 0. Otherwise, you increase the count by 1, wrapping around. So this doesn't really look like a circuit. Right? It looks more like an algorithmic description. And this is very typical of how hardware is actually designed. You can then give this to a tool, like the Xilinx Vivado tool, and it will actually turn it into something that is a circuit with flip-flops in it, and gates and inverters. And then you can map that onto an FPGA. This is what that counter looks like when it's implemented on that FPGA that you saw before. And then you could run a integrated logic analyzer, zoom in, and you will see that it actually counts and does the right thing. So we have a path from algorithmic C-style descriptions as many concurrent processes which orchestrate and communicate with each other, and they get turned into a circuit graph by some tooling through a process of synthesis. And this, in general, can be quite complicated. It could take many, many hours to synthesize a circuit netlist from these algorithmic descriptions. We can also write formal properties and check them. So here's a counter again. And one super interesting thing about System Verilog and about VHDL is that they're the only mainstream languages which really have got very powerful support for formal verification as a key bolted in part of the language. So System Verilog supports LTL, linear time logic. So you can use a temporal logic to specify your intended behavior of the circuit. And here, this property here is one example. It just states that the next value of the counter is one more than the previous one, and you wrap around when you get to the largest value. So you can write this, and then you can write tests to check it. But more importantly, you could give this to a model checker, and it statically analyzes your code, and it tells you, yes, the LTL property you wrote is true for this circuit. And if it was not, it would give you a counter model, and it will give you a waveform trace, which will show you how from the initial state you can get to a bad state that violates that property. So that's kind of cool. We don't really, in the software world, we don't really have that. We have some examples like Daphne and things like that, but none of the mainstream languages that I know of support some kind of formal specification logic like LTL. So that's cool. So let me just give you a bit of insight into the underlying semantics of these languages, VHDL and System Verilog. So like I said, they're based on these concurrent blocks that are waiting to run. So each of these blocks is typically, they're blocked waiting to read in some signal. So when the value in some wire changes and they're listening to it, they run the code in that block. And that code is run sequentially to the end, and it can have state, it has a program counter, right? So here's some examples. There's one always block, it's listening to a wire A. There's another always block, it's listening to wire B. It's another always block, listening to wire C. It's another always block, listening to both B and C. So none of these can fire yet because nothing's happened on B and C. And then I've got an initial block. This is a block which just, when you start running, it immediately runs once to the end and then finishes. So here I am going to monitor what's happening with the values, and I'm going to kick off this chain reaction of block execution. So I'm going to set A to 3. So what does that do? Well, it wakes up the first block, A. And what does it do? Well, the A block assigns to B. It makes B equal to 2 times A. And then, then the A block goes around and it waits for another A to change. Well, now the second block is valid. It can run because B changed and it changes C. So now there are two things listening to C. The third always block and the fourth always block. So the C block will run and it changes D, and then the final block will run. Though I wonder how many times it will run, because it's listening to both B and C. Will it run once or will it run twice? I mean, another way of asking this question is, what is the value of E? Is E 1 or is it 2? I mean, if you know System Verilog semantics, you know what will happen. But it is, a kind of a complicated thing. And indeed, it only runs once. When it does its listening, it's listening to both B and C concurrently. And if both B and C change, the block only runs once. So that's the semantics of how your circuits operate in System Verilog. Got it? This is total madness. What does that have to do with gates and circuits and wires? I don't have an event-based simulator on my wires, on my gates. It's completely unrelated to this circuit I want to build and make. And so I think this is just like some horrible crime that's been committed in history. These languages were made to simulate only hardware. That was their original design time, which is why they're designed to have a model that's efficient for simulating circuits, originally on a uniprocessor. But somehow, over time, people have warped these languages and abused them to not only simulate, but also to produce hardware, to synthesize hardware from these descriptions. And that is how most chips, including the M4 Pro and my laptop, are made. And I think it says something about human ingenuity that you could totally mispurpose something in such a terrible way and still make working chips. So what can we do? What can we do about this? Well, actually, this week, Oops/Splash, Andreas Love has a paper, and his perspective is he looks at System Verilog semantics. He studied it very closely, and he can see all kinds of problems in the System Verilog specification. In fact, the System Verilog specification is contradictory with itself. So it's got many, many issues and problems. And different simulators will do different things. If you run your circuit, if you simulate your circuit and it doesn't give you the answer you want, don't worry, run it of a different simulator, it might work. So his solution is, let's repair system Verilog semantics by trying to modify the standard to make it sensible. And so the always blocks I showed you, they were sane, well-behaved always blocks. In his paper, Splash, he shows you much more badly behaved always blocks. So if you wanted to torture yourself trying to understand the always blocks, you can look at his paper. That is a nice picture of Andreas. There's another paper this week by Junwon Chow and colleagues, and they adopt a different perspective, which is, this is terrible. How can we possibly do anything with this? And they're particularly interested in deductive verification. So their approach is, forget about system Verilog semantics. Let's imagine what would be a good semantics for digital circuits that we can use for deductive verification, that we can use in ROC, in Agda, and Lean. Design that so from the ground up it's sensible, and then retrofit this to system Verilog semantics. And I think that's quite an interesting approach. So let's think, so where have we got? On one hand, design verification is a very difficult, challenging phase of chip design. It takes the longest part of the design flow. On another hand, system Verilog has batshit crazy semantics that are not at all well impedance matched either for design or verification. Has somebody not noticed that these two things are related? They're not independent. Maybe something should change. So what do I want? As someone who wants to design a chip, I would like to have clear, unambiguous semantics, and I want them to be able to support deductive reasoning because I want to be able to do verification and proofs about the circuits that we make. And I'd like to have like a single language which I can write specifications, I can do the implementations, and I can do the verification and proofs. You know, a lot of the work so far in the industry has used different languages for different parts of these processes, and then they're kind of hard to correlate and put together. I also want a language that's got good support for composability. An important characteristic of chip design is that chips are big and complicated and implemented by many people all working together, and there are many challenges to do with scalability and modularity and composability, and your language should have features to support that. I would also like the ability to be able to derive an implementation from a specification, which is, I think, a more rigorous way of trying to make a correct circuit, a circuit that's correct by construction from a specification. I also would like to be able to perform algebraic transformations on these circuits. Often when I'm working with my fellow hardware engineers, we're at a whiteboard and we're drawing circuit diagrams. We've got registers and we're moving registers from one place to another and we're kind of reorganizing the layout. We're thinking in an algebraic, inductive manner about our circuits. But this is not at all directly represented in the circuit descriptions that we write. So I want support for a more algebraic way for describing and transforming circuits, because that closes the gap between what we write at the whiteboard informally and what we type at the keyboard. I also want to be able to take total control over low-level features when I care about it, and not have to worry about them when I don't. So I would have some kind of dynamic abstractions with a wide dynamic range. And I want to have a toolbox of high-level abstractions for common idioms like finite state machines. And to top it all, I'd like to have some tooling which supports all of these activities. And I want it to be scalable, I want it to be fast, and well integrated with existing industry tools. And it would be nice to get a wee bit of help from machine learning. So I've got kind of many digressions. So one thing I've always been inspired for from the 80s, many good things happened in the 80s, especially music. But this is one of the other things. So when I code, I rarely feel like a scientist or engineer. The process seems very ad hoc and informal. And I'm really inspired by the work of Richard Bird and Lambert Meertens in the 80s on systematically deriving an efficient program from a more inefficient program that acts as a form of specification. That, to me, feels like science. So from Bird-Meertens formulation Wikipedia page, here's an example. I'm not going to go through it in detail, just want you to get an impression of it. This is max segment sum. There's a specification of it at the top. It's an inefficient program, but it's kind of obvious that this is max segment sum. But it's inefficient. It's O(n) to power 3. But you can systematically apply transformations to this to get the version at the bottom, And that has got ON complexity, and it will be a good implementation to run on your computer. So I've always been inspired by that, because you have a fundamental connection between your implementation and your specification. Your implementation is correct by construction for this flow. There's nothing to prove. If only we could design hardware like this. And these are there's a diagram on the Wikipedia page which shows the various laws that are applied in each step. So I thought that was really good stuff. Maybe back then that was hard to really do for large software systems, but still a great idea. So, a little bit of functional programming history. So around about 1984, after spending time with John Backus, this is inventor of Fortran, Mary was inspired by John's FP functional language. And what she did was to create a version of it for hardware design called MuFP. So it's a long time ago. And what's cool about this is she makes a direct connection between the concepts and idioms in a functional language and hardware. Composition of circuits is just directly corresponds to function composition in a functional language. Yeah. You can then put circuits in parallel, and you can apply and you can replicate circuits so that the thing to the right will be a map. And it was really, really, really nice. And then you can bend a wire back with a delay to get sequential circuits. But especially amazing was that there were algebraic properties that applied to FP descriptions, these kind of APL type things. And that let you transform program circuits, change their complexity and their resource usage in a kind of systematic manner. And I thought that was really inspiring. And it reminds me a little bit of this Bird Meertens view of the world, and totally different at the time from how everyone else was designing hardware. So then, a bit later, around about 1986, Mary Shearer and Garrett Jones came up with a new language called Ruby. And this is like a relational hardware description language. So some very cool, innovative features to it. So Ruby was based on the idea was you would describe circuits with relations. And these relations composed the behavior of circuits. You see here Q and R are composed by the common wire S, a bit like the system Verilog you saw earlier on. And that was written as Q semicolon R. But you also compose layout. So the R is to the right of the Q. Then you have parallel composition. The Q is below the R. And then you can do loop. And what's fascinating about these descriptors is that they also have algebraic properties. You can use them to transform your circuit to make it more efficient, to change resource usage, and to get a better layout. So I thought that was pretty cool. And being a relational hardware description language, it let you do lots of cool things. You can make an inverse of a circuit. And this might not sound that useful, but there are situations where that's useful as a conceptual device. One place where that happens is when you're retiming kind of pipeline circuits, having an anti-delay is quite a useful thing to have. You probably don't want it in your final circuit, but in your intermediate calculation steps, it proves to be very useful. Super cool stuff. And then you could do these circuit transformations and optimizations very much in this Bird Meertens style. This is something that's done for a systolic filter and some operations that make it more efficient. So a bit later, I thought Ruby was really cool, and it turned out that kind of thinking it can be used to solve real practical problems. So around about 1998, I joined this company called Xilinx that make these FPGA chips that I showed you. And we had these customers whose designs would not fit on the FPGA. Because in theory, when they looked up the data book, there were enough gates and wires for a circuit to go on that chip. But when you run it through the Xilinx tools, their automatic placement and routing, they just couldn't pack the circuit on the chip. And they were desperate because, a multi-million-dollar customer account was about to be lost. And one thing that's important I learned is that people will not change what they're doing unless they're desperate and they have no other path and they have exhausted every other path they could possibly take. So they asked me, Satnam, is there anything you can do about this with your weird Haskell stuff? So I kind of looked at the circuits, and well, I thought, well, this is a filter. It's this block which is replicated left to right, and that if you laid it out in a row, you minimize the wire lengths, and you efficiently pack things. And this thing should be done like a triangle because of the pipelining and so on. So I made a version of Ruby in Haskell. I called it Lava, and this composes behavior and layout. And then when you write circuit descriptions, it generates VHDL at a time, but they also compute the XY coordinate of every gate. And then the customer designs worked, and they were happy. And then I got to do lots more Haskell, lots more Lava. So behind this is these Lava descriptions are these individual gates where we compose behavior and layout. And each gate is in its own coordinate system, in its grid. And when you compose them, the Lava will know the width and height of each cell. And if you're doing like a serial left-right composition, it will shift something along by the appropriate amount, and you get a result back in a new layout grid. Very much inspired by this work done on Escher's fish by Peter Henderson at Oxford. And let me just tell you a little bit about how all this works, because it's incredibly simple. There's nothing sophisticated or clever about it, which is what I think is good about this. So at the root of this, there's a type class for Lava, and it's parameterized in two things. It's parameterized on bit, which represents the values that flow over the wires, and it's parameterized on M, some monad. And then you have like gates like an AND gate, and you have delay. And then the reason for this is we want to have multiple interpretations for our circuits. We want to be able to simulate them, generate lists, draw them, compute things about testability. If you want to simulate these circuits, well, we don't need the monad for anything. It doesn't buy us anything. So we can instantiate the class of the identity monad, and we can model the value in wires as just being lists of Booleans. And then you get the obvious descripts. Implementations for inverter just maps the Haskell not and to, and delay just takes infinite lists and adds an initial value false on top of it. And then you can directly in your repo in Haskell simulate these circuits, which I think is very, very cool. I didn't have to write a simulation framework or an event-based simulator or whatever. You run these descriptions directly. And this is how the previous NAND gate, this is how you do it. And when you run it, it gives the correct implementation. And then there's another instantiation you can make. This time, I'm going to use a state monad to help build up the circuit graph and keep track of the nodes and edges. And then when you run this, you get some system Verilog or VHDL from the output. And then the other cool things are you can model loops just as regular top-level Haskell functions because we have monad fixed. So we just output wire and put it in input. And notice at the bottom, the C occurs on the left and the right-hand side of the monadic byte. But that's not a problem. We have lazy evaluation and we have monad fix. As long as you only consume a finite amount of the output, this thing works. And you can sort of simulate sequential circuits. You just run these things. There's no interpreter or anything else over it. And I think that's such a beautiful, that's such a beautiful thing. The real Lava type class has got other things in it to let you do efficient implementation for Xilinx FPGAs and layout combinators. So let's see an example of this. In this example, I'm going to make use of Lambert, thank you, orthotope array for letting me have vectors whose sizes I can track at the type level. So it gives me like dependently typed vectors in Haskell. And I'm going to do one of my favorite circuits, batches by atomic sorter, which you're going to see in several forms in this presentation. And what this is so this is a sorter, which is a network sorter. This one takes 1, 2, 3, 4, 5, 6, 8 values, and after it and each node is a 2 sorter. It will sort 2 values, and then if you push left to right to its network, at the output you'll have a sorted version of the inputs. And it's built with a butterfly of a merger, which is what's on the right, and 2 smaller sorters. So you can sort of see that structure there. And we can just keep inductively applying this process until we get to the base case and you get the picture that you see on the previous page. So the 2 sorter, the base element, we can write in our Lava hardware description language using par and swap, and we'll use a subtractor and to compare A and B, the 2 values, and then we'll have some multiplexers so you can select the bigger or the smaller. And when you lay it out in the FPGA, you get this nice layout for the 2 sorter. And the other thing we need are a bunch of divide and conquer combinators, which take a big problem and break it down into 2 sub-problems, solve those, and compose a result. And one nice example of that is something called interleave. What that does is it takes some high order parameter R, some circuit, and it creates two instances of it, one laid above vertically the other. And it takes the input and sends the even wires to the bottom R, the odd wires to the top R, they do their stuff. And then at the output, you undo the even-odd split. And you define it by unriffling to R. Riffle 2 is another high order combinator which does the vertical stacking. So we're going to use this a few times in this presentation. And then there's another one called evens, which takes some circuit that takes two inputs and two. Oh yeah, one thing I'd like to emphasize about interleave is that you can only apply it to even-sized inputs, and that's enforced by at the type level, at the dependent type features that we get from Lennart's library. So evens takes a circuit that takes two inputs and two outputs, and it just replicates it across an input vector. But the input vector has to be of an even length for this to work, and that is enforced at the type level. So then how do you make a butterfly? Well, we can do a nice dependently typed butterfly, and we could create one instance of it for degree 1, and that would just give us a 2 sorter. That's what sorter takes 2 inputs. And for a larger butterfly, we interleave 2 smaller butterflies and then apply evens at the end. And this will give us batches bitonic merger. And when you run it, it produces a system Verilog where the XY coordinate of every gate has been automatically computed for you, even though you didn't have a single XY coordinate in what you wrote. And then when you give it to tools to place and route, this is, for 8 input sorter, this is the picture you get. And I think there the butterfly pattern is clearly evident and looks similar to the original picture that I saw, which I think is quite beautiful and nice. From these simple algebraic descriptions with beside, below, par, etc. You've composed behavior. This thing will sort numbers when you put them in, and you get a nice compact implementation of the sorter on the FPGA. This is a bigger sorter of 64 inputs, and this is what it looks like on the FPGA. It looks like a solid rectangular block, and if you sort of zoomed in, you'd see the nice wiring pattern. And this is one that's 128, and if you zoom in, you get a nice wiring pattern. So most FPGA circuits don't look like that. You can't look at the layout, and because the place and route system will just pick some place where it thinks is the best place to put them. So this is the same sorter, but with all the layer information erased, and you can see, it doesn't have the nice structure that you saw before. And if you put the wiring pattern on top of it, where is your butterfly? Butterfly's been squished. It involved a bit of Haskell extensions to make that work. And thank you for the plugins, Christian. And I got some help from some people for writing this code, because I wasn't clever enough to write it myself. So thank you, Dominic, and thank you, Lennart. So you could, I've got a confession. You could have written interleave in C++. And C++ will, at the type level, will statically at compile time check to make sure that you give it an even-sized array, and if you don't, it will give you an error message. So you can write functional programs really in any language. So what does it mean to be a functional programmer? Why are we all here? What is it that binds us together? Well, I think being a functional programmer is more than just what I type into VS Code. To me, being a functional programmer speaks about shared values, about how we write software, common idioms for programming, the design of libraries, and a special network of kind of like-minded functional programmers that we hang out with. So I am a functional programmer, not because of the company that I work for. I am a functional programmer because of the company I keep. So thank you all for keeping me company this morning. So now let's get back to chips and try to verify chips. So at my previous company, Grok, one of the tasks I had to do was to verify a special type of network switch called a BNS network. So what a BNS network will do is it will take some n bits in, 32 in this case, and then with some control bits, it will permute the output. The output will be a permutation of the input. Like, for example, you could reverse. The output could be a bit reverse of the input. And if you go to the Wikipedia page on cross networks at the end, you see a nice picture of an 8-input BNS network. So my job was to formally verify the implementation that the engineers had done of this in System Verilog, which is gnarly and complicated. So I thought, how would I do this? Well, I've got to have all the tools I need, because I know how to express a BNS network. It's a butterfly network, and so I could do its implementation as even swap, and an interleave of two smaller BNS with even swap at the output. But that's not what the engineers wrote at my company. So how did I verify their System Verilog code? Well, I had this multiple interpretations for these descriptions, and one of the interpretations I have is I can make a circuit draw itself to generate some SVG. So I wrote this description, I instantiated it for size 32, and I drew the diagram above. This diagram is the formal specification, right? The goal, it is the source of truth. So you look at that diagram, you compare it to a Wikipedia page. As long as you trust the person who did the diagram on the Wikipedia page who knows what we're talking about, this is the formal spec. Now the goal is, does this picture correspond to what the engineers wrote, right, in the System Verilog? Well, how could we do this? Well, another interpretation of this is to make it generate some System Verilog. So it can actually generate some System Verilog code. And that System Verilog code is just a textual representation of this picture. It's isomorphic. It's the same thing. So now I've got two System Verilog bits of code in my hand. One is basically that picture, but in code. And the other is the gnarly, complicated System Verilog that the engineers wrote. So that with these two programs, I can run standard industry tool called a logical equivalence checker. It's a formal verification tool. And it takes two circuits, and it can tell you if they're the same or not. And the system, I ran that tool, and the proof went through, and it verified that the engineers' implementation matched the System Verilog code that I generated. The System Verilog code was isomorphic to the picture. So I had done the verification. So that was kind of like cute. It's not often you get a picture that acts as a specification and then you can make a proof go through. All you have to do is believe whoever made this picture on the Wikipedia page knew what they were talking about, and you had to trust them. But let's look at that diagram and all the colors and wires that in there. It looks kind of familiar. I wonder who actually drew that diagram. Maybe there's some circularity here. So I showed you how to use these wonderful combinators to do circuit implementation and layout. You can also use them to generate code to run machine learning compilers. And one of the operations that occurs commonly at the end of most machine learning inference pipelines is something called top K. It picks the top N features that are most likely for what you're looking for. So let's see if we can build this using the same combinators. So we need a two-sortrix, and we can write a two-sorter again using the same combinators, except this time, this is code that's going to run on a machine learning chip. So when you compile it, you get some MLIR code, which is a machine learning framework for compiling machine learning programs. And it's expressed in terms of reduce min and reduce max operations over tensors. And then you can create a bigger version of this, the butterfly, and when you generate code for that, you get many, many instances of these two sorter bits of code all stitched together in the butterfly pattern in this MLIR. And then when you run it on the chip, the thing is now doing sorting, all the values going between the memory and the VXM. So that's kind of cool. The same source code for these combinators gets used in one way to make the chip, and the other way to produce programs that run on the chip that it was used to make. I think that's a little bit mind-bending. I think it speaks to the power of these combinators, these high-level, higher-order abstractions. They've just got so much use and utility and reuse. The pictures of the butterflies that you saw here, you'll see them again in a paper tomorrow called Fools Seldom Differ. It will be presented by Craig Roy, but it clearly has Conrad McBride's fingerprints all over the title. This is the picture that you'll see that, and you'll get the full treatment tomorrow. So we'll have another digression. What was I going to say about Steve? So let's talk about Steve Hand, and he is a well-known systems researcher. And he teases me rotten. He says, Satnam, for someone who cares about efficiency, about low-level code and optimizing circuits, why are you programming in these functional languages where you know the value of everything and the cost of nothing? And you just can't understand why I love Haskell and all these other functional programming languages. But I think it's because I've done all this low-level work that I love functional programming. I love Haskell, because these languages give me the tools I need, and lets me build up the high-level abstractions I need, so I can do these low-level optimizations and remain safe and avoid errors and mistakes, because I have the guardrails of the type system to keep me on track. So what I would say is, and I think maybe what makes it different from Steve is, I love programming languages not for what they do. I love programming languages for what they are. And I think maybe that's what makes me a PL person. So let me tell you about another functional language which I have nothing to do with the design, but I think it's like the best example. I think it's the best hardware description language we have in the world at the moment. Right? So the most fit for purpose thing that I think has ever been devised. So with languages like Lava, and there's many other languages that are similar, they're fine for doing structural design where you snap circuits together and design kind of in the small. But as soon as systems get large with many modules, I think things start to fall apart. And then you don't really have any help with control logic, finite state machines, things to concurrency, race conditions. There's just so much more that you need to worry and take care of. And the Bluespec language, I think it is the best answer to all of these things. And I was trying to work out roughly when it came around. I think maybe around about 2020. Here you see a picture of Arvind, who's one of the main people behind Bluespec. Many other people were involved as well. And so lots of good things with Bluespec. So one is Bluespec borrowed heavily from Haskell. So it has all the loveliness of types in Haskell. You have it in Bluespec, and at that time even more, because you had support for dependent types. You had two surface languages, one which looked like Haskell, which I really like, and one which is made to look a bit more like System Verilog to try and convince and trick real hardware engineers to use it. And at its heart, semantics is based on guarded atomic actions, which is really a super powerful feature to let you do scalable, race-free, correct hardware description. So I can't do justice to all of Bluespec, so I'm just going to give you a wisp of a feeling of what it's like. So here's again a running example, a counter. And notice in Bluespec, you have an interface to the counter, and it's got methods, which might remind you of methods that you have from other languages. And in the implementation, you have some state. Here, the state is the value. So that you see the register there is created with an initial value 0. And what can you do? You can read from a register, you can load a register, and you can increment a register. And what's different from System Verilog is that you can break up, you have different bits of code which operate on a shared state, write them in different places, focus on just what that bit of code does, and then Bluespec will stitch things together itself and schedule them in some way that's totally safe, that avoids race conditions, etc. If you had to write that in System Verilog, you are the scheduler. You have to write all that code, and it all gets written in one place, in one block, with no modularity. So that's already a huge advantage. So what's the semantics that's here? Well, there's a lot of questions you might have about how that code runs. Can read and increment be invoked on the same clock cycle, or do they conflict? And if so, does read return the pre-increment or a post-increment value? Can load and increment be invoked in the same clock? If so, is the final value in the counter the load value itself, or the load value incremented? And can read and load be invoked in the same clock cycle? If so, is the read value the preload value or the post-load value? These are all things that you should probably worry about this code. All these ordering questions are made precise by the serialization of atomic transactions, which fixes ordering on the methods. Without more information, the compiler will choose an ordering that's guaranteed to be functionally correct, so no race conditions, and it will inform the user of the order chosen. Or the Bluespec user, through annotations, can specify any desired static ordering and conflict semantics. So Of course, you could do complicated things as well. And the butterfly that you saw before, you can very nicely write that in Bluespec as well. And this is some of the code of, this is a complete code of how you would write the butterfly. And at the heart of it, you can see the base case and then the recursive case where you make a big butterfly out of smaller butterflies. And for me, one of the key benefits of Bluespec is it lets me reason in a modular manner. In the world of software, we're used to getting A to work and B to work, and we kind of hope that the composition works. But in the world of hardware, that never happens. We have all these protocols and transactions over the bus. But Bluespec gives you back modular composability in a way that we kind of have in the software world, but we never really had it in the hardware world until Bluespec. So at Google, the first TPU chip that I showed you, Lambert and I worked on it. We wrote it entirely in Bluespec. I think it was a huge success, and the code looked wonderful, and the chip came back and worked first time. Mike Agda was the person who led that project, and he's now still doing machine learning chips. He's got a startup now called MatX, and they're making some they're in stealth mode, they're making some fancy, another machine learning chip, and they're still doing it in Bluespec. You might think Jane Street is a company that makes nice t-shirts. And the t-shirts are very, very nice. But they also make a hard description language, a functional hard description language. So there is a language called hard camel. Of course, it's no camel. This is what a running example counter looks like, and it generates the following system Verilog. Now, going back to Lava, that was a DSL. It was a library in Haskell, and as a user of DSL, you know all the problems of DSLs. But it would be nice if you could directly write some Haskell and have a compiler that takes the Haskell, parses it, and then turns it to a gate. Well, that's exactly what the Clash system does. And Christian and co, I've been doing this for a while, absolutely fantastic work. This is an example of a binary to gray converter and a gray to binary converter and how you would write it in Haskell, and the Clash system will take this and it will turn it into gates. Super cool. But it gets cooler. One thing I've always worried about functional programs in Haskell is I can never prove anything about them in a systematic kind of manner within the language. But we have liquid Haskell now. With liquid Haskell, we can prove things about a program. So why not connect Clash and liquid Haskell together? So you can write directly in Haskell, produce circuits, and then use liquid Haskell to do proofs. And the Clash people are doing exactly this. It's early stage work, this is a theorem about which says if you do binary to gray, gray to binary, it should be an identity function. You can write that in liquid Haskell, and you could give a proof. It should remind you of Bird Meertens or whatever, and QED, it kind of works. So this is like new work that's just starting, but I think it's kind of an interesting, promising approach. I'm surprised by how far we can really go. Then I would say at the frontier of new hardware description languages is a language called Filament, done by Ratchet Ningham, who's now at MIT. And the cool thing about Filament and the following languages is that in the types, you can say something about the temporal properties about circuits, which then lets you build up an IP catalog of circuits and compose them together in an efficient way. I don't have time to do justice to how it all works, but if you're into hard description languages, check out Ratchet's work. A quick digression for the functional programming PhD students in the audience. When you're doing a PhD and you're working on some proof or some niche, narrow thing, it's easy to get despondent and wonder, why am I doing this? How is this connected to the real world? This seems so academic and obscure. Well, as someone who came from the PL world, did a PL PhD, one thing that's clear to me is that the PL PhD, it gave me a huge toolkit of conceptual mechanisms for solving problems, and being able to apply the techniques that I learned as a PL person to a wide variety of areas, to not just programming languages and compilers, but in systems and Kubernetes and all kinds of things like that. So I would say even when you're in the depths of a very narrow thing in your PhD, remember you're getting training, which is making you a more general problem solver, and that will come evident over time, and will have a range of applications that you don't yet realize. Another way we have tried to do proof, right, for these in a language for circuits is to just use a proper theorem prover. And Google had this project called Silver Oak. It's not on GitHub, where we used Rock, and we made a DSL in Rock, and we implemented circuits, proved properties about them, and verified them. And I had very good help from people that knew how to write Rock proofs very well. And we do the same type class tricks in Rock that we did in Haskell. And we took an AES block, and we did a spec implementation and proof. And the proofs were they were quite hard to write. So how can we make proofs easier to write? Well, let me just give you. I'm going to show you something, which is going to get me in trouble. Does this come up in this? Okay. So what I want is, at Grok, I started to describe circuits in Agda. And I wanted some help to do the proofs. So what you see here is VS Code with an Agda lemma in it. It's any all lemma, which is De Morgan's law listed to list level, from Phil Wadler's Agda book, is at hard exercise. And I wrote a wee program which connects to an LLM, and at the bottom you see the LLM trying to come up with a proof. So I just give the lemma in Agda to Opus 4.1, and then after a few iterations, Opus finds a proof, the compilation is successful, and then I double check it in my ID, and it's worked. I thought, oh, that's quite cool. Maybe we can actually get machine learning to help us actually do proofs for our circuits. So let me return to my presentation. So that would be cool, because if you could get a theorem prover to help do that, you could try and do these circuit proofs, and then when you get to a certain level, you can shoot the aliens down by just dispatching to an LLM how to do the proofs. And I'm really inspired by the companies that have won these at the Maths International Olympiads gold medal. DeepMind got a gold medal this year for the International Maths Olympiad. So did OpenAI, and so did this tiny small startup of about 18 people in Palo Alto called Harmonic. So, and their approach involves using Lean. They took the problems, they expressed them in Lean, and their engine, their machine learning model, consumes Lean and a Lean lemma and tries to give you back a proof. Absolutely amazing stuff. It's almost actually. And what's cool about this is that you can check the result of the LLM to know if it's lying to you, if it's hallucinating. Because you can take the proof it gives you, you can give it to Lean, and Lean will tell you whether it's correct or not. I think that's like an amazing property. And so it would be cool if we could use this to make hardware better. And I think what we should do is take, in Lean, build up a library for hardware design, but we should not base it on the batshit crazy semantics of System Verilog. We should not base it on Mealy-Moore machines, the machine-coded sequential circuits, or Kripke structures that are used for border checking. We should base it on a sensible semantics for circuit design, which has been proven to work. So I think we should take Bluespec's semantics and code them up as a library in Lean, and use that as a basis of how to design hardware, verify hardware, do proofs, and do implementations. So guess what's happened? I'm done with these megacorps. I'm not working for them anymore. Next month, I'm going to join Harmonic to do exactly that. So stay tuned. Functional programming and hardware design has started a new chapter. Thank you for your attention.
Thanks, Satnam. That was such a great talk. Everybody's stunned and has nothing to say. So that was an amazing talk. I really liked that go over the history. But of course, it was also a very depressing talk, because you explained how back in the 1980s, Mary and Kuhn and you and all these other people already knew how to do all this. And since all that time, people are still doing it the wrong way. So you talked a lot about the technical things. I wonder if you would say a little bit about the people side of it. You did touch on this, yeah. But I wondered, what do you think has been the most successful human engineering of this to get people to use it? And B, how do all the young people in the room carry that forward?
So I'll answer this in reverse. I think a really great example of doing things differently for verification is the ACL2 system, produced at University of Texas, which has been used to do a form of verification of large chunks of x86 style processors. It's not used to design hardware, but it's used to verify hardware, and that's all based on functional programming. Why is it like this? Well, hardware engineers fear abstraction. Abstraction is not their friend, it's their enemy. So when I worked at last company, Grok, there was a situation where somebody had used a struct as a type on the interface of a module, because these signals were grouped together logically, so you should have a struct. And then in code review, that got rejected, because lots of hardware design engineers hate a struct. They don't know what that means. How are the wires laid out? Will some inefficiency be introduced? And the person who wrote that code had to delete the struct and replace it with the individual wires that made it up. Right, that was this year, right? This was not in the past. So engineers fear abstraction because they think it's going to make their circuit inefficient, it's going to add extra gates, it's going to add extra logic. And that's just a cultural, social thing. Engineers are conservative. If you make a mistake and you tape out your mask set, you've lost millions of dollars, you've lost 6 months, and you've lost your competitive advantage, and that chip may no longer be viable. So there's an inherent conservative, these people are inherently conservative. However, I think there's hope, because I think the verification pain has got to such a level that they have to do something different. And that's why I highlighted that about when I worked at Xilinx on Lava. It's only when people are so desperate and they've tried every other approach and it hasn't worked that we'll try something different. I think we're there with chip verification. People are so desperate that we developed a different flow that could give high assurance, proved correct, formally verified, proof by induction, proofs of big complicated circuits. I think people would buy into it because there is no alternative.
So you mentioned ACL2. I'll just tell you an anecdote that I was told by Jay Moore, one of the developers of ACL and ACL2. He just put up this little graph of what they could do. It started very tiny, right? But it went up by 1.5 every year, Moore's law. And so by the end of it, right, they were verifying entire computers. And all you need to do, I think that if you look at the progress of Haskell, it's been the same thing. You just do something good, teach your students, let them out in the world, and wait 30 years.
Thank you for your question, and thank you for the NAOL LMFO.
Hello. A more technical question. You talked about having a very simple system to assign the XY coordinates. And that gives you a very structured representation if your input was very structured. How does it, you might not be able to fit this into your space that you have. How does it interact with like optimization, where you might want to actually squash stuff into?
We just have layer combinators which will, if something's too wide, then you have a combinator which will break it at some articulation point and bend it around, or snake it, or whatever. So you have a toolkit of things which lay things out as you want them in any way. Mm-hmm. I didn't have time, but I was going to do Escher's fish diagram, if you might be familiar with, and I was going to lay it out on a chip to show you the flexibility of layer combinators. You could definitely do that.
Mm-hmm. Thanks.
Hi, but there's a tension there, right? Because when I'm thinking of a circuit, if I want to use all the high-level abstractions that functional programming gives me, like in some of the examples you gave, I might write down something that if I normalize that fully, there's no 2D structure to it at all. It's not even possible to lay it out. So there's a tension between wanting to control the layout and wanting to describe circuits at a level where I can't really see as a human that it's going to...
So in a far too small font in a real-time class, You had a bunch of combinators have got no layout associated with them, so they just get code from that is automatically placed and routed by the system. And you have other combinators that do layout. So if you use Kleisli arrow, I didn't define Kleisli arrow. It comes from control.monad, and you compose that. No layout is computed. You have to use my special, greater than minus greater than, and so you get to choose what you want to lay out and what you don't want to lay out. And so you can do the right thing at the right time. You have low-level control when you need it, and high-level control when you want it.
Okay.
Thanks for a great talk, Satnam. You were suggesting that Bluespec is like the state-of-the-art specification language here, but you showed these examples in Haskell where you're making use of dependent types. Does Bluespec support that functionality as well? Oh, so you can do all the static guarantees there as well.
It had those features, well, thank you, Leonard, long before we have them in the form we have them in Haskell, yeah.
Oh, great, thanks.
So Satnam, thank you. But you're kind of presenting it as if hardware design is now a solved problem, right? Functional programming has conquered the world. But actually, it's still pretty hard. It's still pretty hard to build really big chips that work, and it's hard enough just to get them to give the right answer, let alone be laid out nicely in with the right kind of delays and power consumption, all that kind of thing. So where's the next frontier, and is functional programming going to help with that?
Well, I mean, so I think some of the layout stuff, and that's kind of cute, but most people don't really do layout unless it's for some super critical thing. Though I did work on my last company, I did actually work on something that needed that level of layout control. So I think the most important and challenging problem in hardware design is verification. Right? It's what's stopping us from innovating new chips, adding new features, trying out more powerful optimizations, because we don't have the verification to keep us on track, and every time we need to re-verify, it takes too long. So people focus too much on trying to design languages to express what you want to compute. Well, I think we need to think about what we want to specify and we want to implement. Specify, because I think the role of machine learning is going to become more and more important for hardware design as we use LLMs to generate circuits and properties and help with proofs. And for verification, I think we need to do something different from the kind of the model checking that you saw before for the counter. It uses the model checker, but these model checkers will run out of capacity when there's too many state bits in your circuit, and suddenly you've fallen off a cliff, you can't verify anymore. So I really think we need to look at deductive reasoning techniques and make those viable. So that's what I think the next step, right? Take something, a language that's got successful kind of scalable semantics that have been tested and shown to be working, like Bluespec, encode them in something like Lean and produce like a DSL for hardware, which you can use for design, implementation, and specification. That'll be a new thing in the world that we don't have today. It isn't solved, but I think it's a path to a better world.
Satnam, we wrote a fun paper about 15 years ago about reconfigurable FPGAs.
I remember that.
And I was just wondering, what happened to the reconfigurable part? Because it seems that the use of functional programming to quickly specialize and have a really dynamic world might be a thing, but it seems to have disappeared now.
Yeah, I mean, I think, again, if you say to an engineer, you produced this beautiful circuit that you spent 5 months verifying. Oh, by the way, at runtime, I'm just going to totally mess with the gates and totally rewire it as it runs. I mean, this is not a Python program. This is like a circuit. You can't be just like rearranging it as you run. So people are kind of scared of that. You really need, I think that's a great use of form of verification to prove that you only reconfigure in a sensible kind of manner. And then, in a previous life when I was academic, we actually had research projects, people like Tom Mellon and so on. We actually did proofs that circuits would reconfigure in a nice manner. But how many people in the world can do those proofs and believe in them? So I think dynamic reconfiguration was hard to sell because it was hard to verify.
Hi, Satnam.
Hi.
Max New, University of Michigan.
Hi, Max.
I had a question about your example using monad fix. So you were expressing the recursion in the circuit using value level recursion in Haskell. So I could see how that would work for a simulator, but you're also able to get a hardware description of the circuit out? Yeah. How can you do that? Because when you use value level recursion, don't you lose you can't tell that it was construct recursively?
No, you can't. Over coffee break, sit on my laptop. I'll show you the implementation.
Okay, thank you. Perform something, unsafe perform something?
No.
No? Okay.
You think too lowly on me. If I was going to use unsafe perform, then I wouldn't even need the monad because, right.
Hi, Satnam. This is a very random question, but I was wondering if you have thoughts on the costs imposed by development cycle costs imposed by place and route. That seems to be the biggest bottleneck in people iterating more quickly on getting, say, performance feedback and lots of other things. I know it's different than what you're talking about, but maybe you have some thoughts.
Yeah, I mean, place and route for FPGAs can take hours. It can take more than a day, right, for a chip design. But that's not something I really kind of worry about. I think simulation for verification is much harder. Those runs can be longer than the kind of place and route runs. So that's the friction for people, right? They've got an idea, a test or property they want to check, and it takes. It could take a day to run the simulation, or your model checker runs for ages and then it gives up because it runs out of capacity. So I think the iteration that's the most painful is the verification iteration, not the implementation one.
Hi, Satnam. I'm Dan from the University of Southern Denmark. I was just concerned that your Haskell programs were too beautiful. And I was thinking about how, like, Robert Frost can say in 10 lines what I could not say in 100,000 words. So I wonder if that is an element at play that, you know, functional programmers, I mean, you can put a lot of thought and express something really beautifully in a way that you can easily verify, but that most engineers might not be able to really wrap their hands around. Is that an issue in this space or not at all?
I love the programs for what they do. I love the programs for what they are, and I think they're beautiful descriptions, and I like them anyway. And I don't care what the engineers think.
Okay, I'm afraid we'll have to stop questions there. Let's thank Satnam for a fascinating talk.
Thank you very much.